I mentioned in the video on homotopy, the previous video, that we would use that concept to build up to something called simply connected. It's a new type of connectedness. And the idea behind it, or the reason we like to use it, is mostly because it helps us discern topological spaces from one another. Just like we could use connectedness and path connectedness to do that, because they are themselves topological invariants in the sense that if you have one space that's connected and you apply a homeomorphism, or really any continuous map, you're going to get another space that's still connected as your image. And the same goes for path connected, right? Continuous image of path connected is path connected. And it's going to turn out to be true for this property, which I haven't defined yet, called simply connected. And so it's going to give us a way to discern spaces from one another. So to just build up to there, let's remind ourselves that we know examples of spaces that are automatically not homeomorphic. And remember this symbol, well, without the slash, it means homeomorphic. So with the slash, I'm saying these spaces are not homeomorphic. By the way, I haven't specified the topology here, but I'm supposing it's, let's say, the Euclidean topology. And these are not homeomorphic because one is connected, the other is not, right? Here's R, it's nice and connected. We can prove that if we want to. But if I take away 0, say 0 here, or really if I take away any point, right, I slice that and all of a sudden it's disconnected into a left half and a right half. And therefore they can't be homeomorphic. If they were homeomorphic, well, continuous image of connected is connected. Right? So if I applied the supposed homeomorphism to this space, it would have to still be connected, but this space is not connected. So no homeomorphism can exist between those two spaces. Similarly, we could use path connectedness to detect spaces that are not homeomorphic to one another. So you could take the space T, which I'm defining as this thing, just the set of all points in R2 of the form x comma sine of 1 over x. So it's like the graph of sine of 1 over x. Note my domain is the half open, half closed interval from 0 to 1. And I'm going to say that's not homeomorphic to this space. Really small change. I think I've shown this one before. This set, the one I'm highlighting right now, is called the topologist's sine curve. And it's what you get by just appending a single point, that red point at the origin, to the rest of the set T. So what do we know? We know one of these spaces is path connected, the other is not. In particular, T is path connected. Take a minute to think about why it's path connected. There's a really quick one-line proof that it's path connected. Pause the video if you need to. Spoilers, here it is. This space is path connected because it's the continuous image of a path connected space. Right, if you look at the half open, half closed interval from 0 to 1, that's path connected. You take the continuous image, right? So this is a continuous function on the interval from open 0 to closed 1. That's kind of why I left out the point 0. It wouldn't be defined there, it wouldn't be continuous, but it is when I leave it out. So that's a continuous function. I apply it to that interval. The image of that should be continuous as well. And then we can say something about like graphs of continuous functions. Anyway, that ends up being path connected. However, appending the origin gives me the topologist sine curve, and it's no longer path connected because whereas when I was working with the yellow space, I could, get between, say, this point and this point in a nice continuous way. Now I can no longer get from the red point to really any other point in T, because how am I going to wiggle around in this yellow space in a sort of finite amount of time? How am I going to actually connect up in a nice way, nice continuous way? And the answer is you can't do it. So by virtue of that, you have a space that's path connected, you have a space that's not path connected. Path connectedness is preserved by homeomorphisms. So if these two spaces were homeomorphic, they would have to have the same topological properties, right? They would have to either be both path connected or both not path connected. In this case, one is path connected, the other isn't, so they can't be homeomorphic. And that's all you need to say. What about something like this? So let me actually change this so it's a little more friendly. Let's make this open on this side. Why isn't this interval homeomorphic to the circle, which we call S1? And you might look at it and be like, well, I can convince myself it's not homeomorphic. I know homeomorphism means I need a function that's both continuous, bijective, and its inverse is continuous. And in this case, sure, I could, wrap this interval up little by little and kind of pull this side around so that, it looks like this, and then keep pulling it until I get basically a full circle. So a nice smooth deformation, or a nice continuous deformation. Seems like it should work, but you can't go backwards, right? You won't be able to go backwards in a continuous way because that would involve tearing the circle. Tearing is not a continuous operation. So like that's our intuition. So like if I wrote down a particular map, e to the 2 pi I x, which you would imagine actually does wrap this around. So the point, 0.1 or something might map here. The point 0.9 might map here, and you'll get this really nice connection. I think we've seen that before. And so it's bijective, it's continuous, but it's not, its inverse isn't continuous. But really that just shows this one function isn't a homeomorphism, right? This hasn't shown that a homeomorphism can't possibly exist. I'm just saying this one isn't a homeomorphism. So how can I show a homeomorphism that is actually impossible? So for a general function f that maybe does something completely different, rather than wrapping the interval around the circle, you could do infinitely many weird things here. How do we know one is not the other? What's going to happen is this is going to turn out to be simply connected. This interval, whereas this, the circle, is going to be not simply connected. And I haven't defined that term yet, but I'm trying to just build up our notion, our understanding of connectedness. The idea that, okay, yeah, we've seen two spaces that were connected and not connected, so they couldn't be homeomorphic. Then we had path connectedness, which was even stronger. And now we have simply connected, which is going to be even stronger than path connected. So again, like you'll have, if you have a path connected space, what can you say about it being simply connected? Well, not much, but all simply connected spaces will be path connected. So there's a nice containment there. You could draw a little picture and be like, okay, if I have a simply connected space, let's make a diagram like this. Here are all my simply connected spaces. Simply connected automatically implies path connected, but there will be some examples that are path connected and not simply connected. And then similarly, let's just write C for connected. There, for example, the topologist sine curve is connected but not path connected. But everything that's path connected is automatically connected. So they're kind of nested. And simply connected will allow us to detect differences between spaces like this. The gist is you're going to be detecting holes with it. So there are no holes in this interval. There is some weird hole in the middle of this circle. So that's what simply connected is going to detect. And then you might ask some other weird questions like, how do we know that S2, which is the sphere sitting in R3, is not homeomorphic to the torus, which we call T2? And the answer is going to be similar. It's going to rely on simply connectedness, but it's going to break your brain a little bit because you're going to look at the sphere and be like, oh, just like the circle, the sphere has a hole in the middle. Right? When we say sphere, we mean the surface of the sphere, and it's like an empty vacuum in the middle. So you're thinking, oh, okay, well, yeah, there's a hole there. But wait, there's also a hole through the torus. So how are we actually going to distinguish between these two? It's going to turn out that the holes that you see in a torus are different from this kind of hole. And I probably won't get to explain why. You might have to take a higher topology class to see why. But we will be able to make a slightly easier argument. Instead of talking about holes in different numbers of dimensions, we'll have a simpler route. Okay, so all that goes to say, our goal is to be able to detect differences in topological spaces. To do so, we'll need some definitions. So last time we talked about homotopy, what it meant for two paths in a topological space to be homotopic, namely they could be continuously deformed into one another. And we talked about homotopy classes of a given path. So using that definition, and if you forget, I encourage you to go back and review, we're going to be able to define one of the most powerful tools in, well, I guess I'll call it algebraic topology. This will be our first foray into using abstract algebra in a way that unifies it with topology and really brings it to life. So given some topological space and some base point in that space, the base point is going to function as the starting and ending point of our loops. So given a topological space and a base point, we can talk about the set of homotopy classes. And this is exactly what you would do if you had an equivalence class in an algebra course, or anytime you encounter an equivalence class or an equivalence relation, you can talk about the set of equivalence classes. We proved last time homotopy is an equivalence relation. So we're talking about the set of equivalence classes, and we're going to have a little symbol for it. We're going to use pi, and pi has sort of relies on two things. It relies on the topological space, but it also relies on the base point. Okay, so just brief example, if our space was a torus, so that's capital X, and usually in most examples you see, you'll be free to pick any base point you want. But saying that's the base point, x0, means that I'm considering all loops that start and end at that particular point. Again, most of the time it won't matter what point you pick, but you get to consider all manner of loops starting and ending there. So that's the mental picture we're having in our brains. What do we call this thing? Well, if you've looked at the title of this video, you might guess this is called the fundamental group. And I told you we would get some algebra in here, so I'm using the term group in the algebraic sense. It's the fundamental group of the topological space X based at the point X sub 0. Most of the time, we're going to be dealing with spaces that are path connected, though. And there's a really nice theorem that says if your space is path connected, this fundamental group doesn't depend on x0. You can put x0 anywhere you want, and the fundamental group won't change. So in that case, we'll just represent it as pi of x, the fundamental group of the space x. Okay, but I haven't proven it's a group yet. Really, the way I've written it, it's just a set of equivalence classes. Why on earth would it be a group? What's even the group operation? I haven't verified it has an identity or inverses, or that it's associative or closed under this mystical operation, which I haven't defined yet. So really, I should do that, and I will in a couple minutes. But for the time being, we'll just call it the fundamental group. Trust me that it's okay to do. And we'll also define a couple other terms. So a topological space is, here's that word, or that term, topological space is simply connected. If it's path connected, right? So it's a stronger condition than being path connected. That's why we drew those nested sets. So it definitely has to be path connected. And mostly it just has to be path connected so we can write the fundamental group without talking about a base point, because base points are annoying and we like to ignore them whenever possible. But yeah, so you can write pi of x to mean the fundamental group, and we want this to be trivial. Okay, what do I mean by trivial? You'll have to wait and see. If you're used to abstract algebra, I mean, the trivial group is just the group with only the identity in it. But again, we haven't defined what the identity homotopy class is. But we'll get there. And I'll mention one other thing. What does it mean for the fundamental group to be trivial? It means this. It means all loops are contractible. Okay, all that will be explained in time. The first thing I have to tackle is why on earth is this thing a group? So let's start with that, and then we'll talk about the rest. So here's that theorem. And in purple, I've added what I mean by the group operation. It's a little weird to wrap your head around at first. Okay, so we're noting to ourselves, remember that when we're talking about this set of equivalence classes, a set of homotopy classes, if you want to call them that, they're really homotopy classes of loops based at x sub 0. That's how we're defining this fundamental group. So for example, like I drew, right, we're thinking, here's my base point, and what possible loops can I draw in this space? Starting and ending at that base point. But the important thing is we're considering homotopy classes therein. For example, let me change colors a bit. If I have the point x0 and I consider this loop fairly simple, let's call it f. And I also consider this loop a little different, not too crazy, let's call it g. And using the language I used in the previous video, these are both just sort of necklaces that I've draped over a torus, right? Notice they're not wrapping around any weird part of the torus. They're just sitting atop it. And so you could conceive that it is possible to continuously deform one into the other. In that case, we would say that f and g are homotopic. And in particular, they're in the same homotopy class. So f is certainly in its homotopy class. That's always true. But g is also in the homotopy class of f. Because they're homotopic, and the homotopy class is the collection of all paths homotopic to the given representative, in this case, f. Okay, so I'm tossing around a lot of big words. I apologize for that. This takes a while to wrap your head around, no pun intended. But it's really beautiful once you get used to the notation and terminology and all that. So the point is, the thing we're working with here is not individual paths. We're working with homotopy classes of loops, right? So I'm thinking about f and g really as the same object. I'm thinking about them each being representatives of the homotopy class of f. And I could draw infinitely many more things, more loops in the homotopy class of f. They're all equivalent to it. You basically think that they're all the same object. And so we are working with equivalence classes. So when we're talking about a group, we have to define a binary operation on the elements of that group. In this case, the elements are equivalence classes. So right here, I'm saying, okay, equivalence class of f multiplied by equivalence class of g. I'm using multiplied loosely. I just mean it in the group sense of we're combining these two group elements in some way. And the way we combine them is by concatenation. Okay, so it's worth writing that down. This is concatenation of loops. And I define specifically what that means right here. So given two loops f and g, first of all, let's forget about this equivalence class and just look on the inside. Really, I'm just taking individual loops at this point, f and g, based at x0, and concatenating them. So effectively what that means is I'm starting at x0 still, and concatenation of loops, let me give these things a direction first of all. Let's say f was traversed in that direction, and g went like this, back this direction. So how do I concatenate these things? Well, I just traverse the first one, and then I traverse the second one. And what you notice is that concatenation, the red thing, is still a loop based at x0, which is good. That's going to guarantee us closure, saying that if I quote unquote multiply two loops together, I still get a loop. But there's some stuff you have to untangle in the sense that really f was a path, so it's a map from the unit interval to your topological space, and g was as well. And you could think, well, it took me 1 second to traverse f, because we're thinking of the domain as time, so 0 to 1, maybe think of it as a second, whatever unit you like. And it would take me a second to traverse g. So if I walked around them at the same speed, it would take me 2 seconds. And that would be like saying, okay, f concatenate g is now a map from 0 to x, and that's not appropriate, right? This would no longer be a path. Paths are defined on the unit interval for whatever reason. We just like to keep it consistent. So the way we get around this is as follows. Maybe you've seen it already. Maybe you've looked ahead. What we do is we walk twice as fast. That's all this means. The fact that there's a 2 times t in the argument to each of these paths means, well, think about what happens. Let's plug in some numbers here for t. If I plug in 0, okay, so let's think about this piecewise definition. So plug in 0 for t. That means I would take this branch and plug in, well, f of 2 times 0 is f of 0. But f is a path starting at x0. That's our base point. So this has to be x0. So that's good. That says my concatenation still starts at x0. What if I look at time a half? Notice I put closed brackets on each of these, meaning it doesn't matter which one you use, you're going to get the same answer because f composed or f concatenate g is actually continuous, so it's fine to write it this way. So yeah, if you plug in 1/2, you'll either get f of 2 times a half, which is f of 1, from this half, or you could equally well plug t equals a half in here and you get g of 0, right? But in either case, I mean, that's either the endpoint of f or the starting point of g, but they're loops. Again, we're back at x0. And finally, if you plug in time 1, that'll default to this branch of the piecewise function, and we'll get g of 1, which is also x0. So all this goes to say, this is a nice continuous function. It's defined on 0, 1. So this is a map from 0, 1 to x still. Right, because I only needed to plug in 0 and 1 because I'm walking at double the speed. So instead of taking 1 second now, it takes half a second to get around f and half a second to get around g. Therefore, I'm still a path at x0. Ta-da. I've done exactly what I set out to do. I've concatenated 2 paths to give me a 3rd path. Now, what can we do with that? Well, once we do that operation, right, we're taking these 2 representatives, f and g, of their respective equivalence classes, concatenating them, and then taking the equivalence class of that result. Okay, so kind of crazy, but that all works in our favor in the sense that I'm taking 2 homotopy classes, I'm spitting out a homotopy class. Each one had a representative that was a loop based at x0. The result has a representative that's a loop based at x0. So we need this definition in order to give us closure in the group operation. So here I'll just note you get closure from the fact that f concatenate g, guess I don't need the parentheses, is a map from 0, 1 to x. Is what? Well, it's continuous. That was us verifying that no matter what I plug in at the join point between these piecewise branches, we get the same result, namely x0. That's a big reason why we want to work with loops. So this is continuous, which means it's a path. And yeah, it's a path that turns out to be a loop based at x0. So I'll just say is a loop based at x0. That's exactly what you want to say when you're talking about combining 2 homotopy classes of loops based at x0. You want another loop based at x0 as the result. So that's no big deal. But how do we prove the other things about a group, right? You need identity, inverses, associativity. And we could write a formal proof for this, but I'm going to do what topologists love to do, and I'm just going to prove it with a picture. And, this is actually a useful skill to learn. I have some squares drawn here. So let me write what I mean by the identity. What is the identity element of pi of x? Well, let's call it E. Sometimes we use that in group theory, right? To be an identity element, it'll have to be a loop based at x0 at the very least. And its definition is going to be real simple. No matter what time t I plug in, I spit out x0. So the identity loop is the loop that does nothing. Right? Imagine it saying, okay, I start at x0 and I sit there forever. Well, I sit there for 1 second, I guess, as time runs from 0 to 1. And then I end at x0. Ta-da, I'm a loop. Right? Continuous maps like that, or constant maps like that, are continuous by nature. So yeah, it's guaranteed to be a loop. Great. Let me rearrange this here. We'll say define this by this, then the equivalence class of E is the identity. Of the fundamental group, the thing we're trying to prove as a group. So why is that the identity? Well, because I can show that, for example, if I do, what do I want to do first? Let's do F times E. I can show that that's actually equal to F. That's what an identity has to do, right? If you take any element of your group, multiply it on the right by the identity, nothing changes. The way I'll prove this, and it's a kind of hand-wavy proof, but stick with me. The way I'll prove this is I'll say, well, first of all, let's put a question mark here. First of all, this is equal to F concatenate E by our definition of how we're combining these group elements, right? That was right up here. So I want to concatenate these things. How can I concatenate them? Well, they're both paths in my space X. And concatenation means I'm going to traverse F twice as fast and E twice as fast. So let's think about F being here and E being here. So in your brain, you're imagining that, maybe I'll draw this in red. This is the point x0. That's our base point. And I guess this will also be the point x0. And so F is some path, which we're drawing as a line here, but you can imagine it doing all sorts of wacky things. A path from x0 to x0, meaning it's a loop based at x0. And then, okay, again, starting from x0, we do the loop E, which is really the do nothing loop. It's the identity, but and then eventually we get back to x0. I want to show that this is homotopic to F. Because if I do that, if I show that F concatenate E is homotopic to F, that's exactly saying their equivalence classes are equal. Remember, if two paths or two loops or whatever you're dealing with are homotopic, they're in the same equivalence class. Which means it doesn't matter what representative you use, F concatenate E or just F. They're homotopic to each other, so they're in the same equivalence class anyway. Representative won't matter. So that's what we want to show. How do we actually go about doing it? Well, again, F is a loop starting at x0 and going to x0. So forget about these vertical bars. So far, we're just imagining, okay, F is some path, F is some path, E is some path. What we want is a homotopy mapping from F concatenate E to F. And that homotopy, I mean, look at this. Doesn't this look like I cross I? If you imagine this as the interval and this as the interval, and homotopy is mapped from I cross I into your space X. So what we can do is we can say, well, a homotopy has to be a continuous map from basically the unit square to the space. And so how can I make a continuous map that transforms F concatenate E to F? Well, the way I do it makes no sense the first time you see it. It's just by doing this. Okay, what on earth do I mean by this? Well, what I mean by this is that at time 0, what I'm doing is this. At time 0, I'm doing F concatenate E, right? So this is like t equals 0 level. At time t equals 1, hopefully I've made it all the way to the function F. Okay, and then I'm just the path F looping from x0 to itself. Anywhere in between, say t equals 1/2, this is what my map is. My map is this. Well, it says this is F, this is E. Okay, and what's actually happening here? Well, this is like, call it S or something. S equals 3/4. So what's happening is we're spending 3/4 of our time taking a leisurely stroll along F, and we're taking 1/4 of our time sitting at E. Right, so let's draw this on a torus, just so we have something to look at. Here's my big fat donut. I'm imagining some base point. I'm imagining some loop F, which we're going to make simple. Give it some direction. And we're going to have some basically do nothing loop, which I'll call E. And I shouldn't have even drawn it as a loop. It's really just sitting there, but I didn't want to cover over the point x0. So E does nothing. So what are we saying? We're saying first at time t equals 0, what we're doing is we're traversing F at double speed and then sitting at E for the remaining half a second. As we go up, as time progresses, we go around F at a bit more leisurely pace. So we spend 3/4 of a second going around. And then we sit at E for 1/4 of a second. Then we get to say here, right, this is 3/4 into the progression of this homotopic deformation of our concatenated loops. Man, that's a mouthful. But at this point, we're thinking, oh gosh, I'm spending like 7/8 of my time going around F. So I'm going even slower. And I'm saying, okay, yeah, spend most of your time taking a leisurely stroll around F, then sit at x0 for 1/8 of a second. And then gradually keep doing that. Keep doing that. It's a nice continuous thing you're doing. You're just slowing down little by little along F and then sitting at x0 for a less and less amount of time. And then eventually what you're doing is you're just taking F at normal pace. Now it takes you exactly 1 second and you're not sitting at x0 at all. Which means we've constructed a continuous map from F concatenate E to F that is a homotopy. It's continuous. Notice that these endpoints were fixed the whole time. That was a requirement of a homotopy, right? I never strayed. My start point and end point were always x0. And at time 0, I was equal to, the first thing, my first loop. At time 1, I was equal to my second loop. So this is insane when you first see it, but it turns out to be a really handy representation of homotopies. And so let's practice a little. Let's say I wanted to do the opposite. Let's erase this. So this shows me that E is at least a right identity. How do I know it's a left identity as well? Meaning if I take E, multiply it by F, do I get F? Question mark. The answer is yeah. Okay, this time E is going to sit down here first. We're starting with E and then concatenating F on the end. We're thinking, okay, again, I have x0 as each of my endpoints. That's why we like to base everything at the same point. So we don't have to worry about that. And now, how can I define a continuous function that starts basically as the do nothing operation for half a second and then traversing F at double speed? Well, I just gradually spend less and less time doing nothing until I'm spending 0 time doing nothing. And so the way this was presented to me was think about this as developing a homotopy to eliminate procrastination, in the sense that okay, yeah, I'm assigned a paper to write a week in advance. Sure, I could spend the first 3.5 days doing nothing and then spend the next 3.5 days working my my butt off trying to finish this paper. Or I could be a little smarter with it. And I could be like, okay, I'll maybe up here, it's like saying, okay, I'll take like a little 1-day break. And then I'll spend 6 days working on the paper. But I still have to work slightly faster than I would if I just got started from the beginning. And, I was a perfect student and I started working the second an assignment was given to me. Then I can work at a leisurely pace. But that's a continuous change, right? You could imagine any slice of time here, and you're gradually shrinking the amount of time you spend procrastinating in favor of doing work. And so that is a homotopy from E concatenate F to F. Right, so you can say, well, E, homotopy class of E times homotopy class of F is homotopy class of E concatenate F, but E concatenate F is homotopic to F, meaning they are the same. They actually are the same homotopy class. So this is our identity. We still have to prove inverses, right? And again, you could show this 2 ways, but what are we going to do? Well, how do you define an inverse map? First, define F inverse from 0, 1 to X. So it's a path. In fact, it's going to be a loop based at X0. And we're going to define it by the following. F inverse applied to, I guess I should say T here. So we like talking about time. F inverse of T is going to be F of 1 minus T. What does this say? This says if you have some loop F based at X0, say, this is time T equals a quarter, T equals a half, T equals 3/4, then what's the inverse path of F? Well, it's sort of exactly what you would want it to be. It's the same exact thing, but you go in the opposite direction. You go like this. And so now at time 1/4, you're where you were at 3/4. At time a half, it actually matches up. And then once you've elapsed 3/4 of your time on the reverse path, you're exactly where you'd be at 1/4 of your time on the forward path. And so you can sit down and confirm, yeah, if I do like F of 1 minus 3/4, I get 1/4. Right? So it actually works out. We know that the composition of continuous maps is continuous. You can verify that this still starts and ends at X0. So lo and behold, it works. And our claim is going to be that the homotopy class of F inverse is predictably the inverse of the homotopy class of F. So let's show that. Right, what I really want to say then is homotopy class of F, group operation, homotopy class of F inverse. Is that equal to, well, it should be the homotopy class of the identity, right? All right, let's see if it works out. Again, X0 on all the corners. We're not moving that base point, so these got to stay fixed. Again, I'm concatenating 2 things. Right, so we're thinking first, okay, the group operation says to multiply homotopy classes, I first concatenate their representatives and then take the homotopy class of the result. So here's F inverse. And I want to get up here to E. How on earth do I do that? Well, what could I do? how about this? How about, what should I use, purple? Okay, well, let's look at what the concatenation looks like. For this example, the concatenation, I'll do a highlighter actually. Concatenation looks like traverse F at double speed, backtrack traversing F inverse at double speed. Okay, what if I did this? What if I traversed F really quickly, but then like stopped at 3/4? And then I just sat there for a while and procrastinated, and then I reversed my trip. Okay, I mean, that might work, right? And what if I just went to 1/2 and then reversed my trip? Or I just went to 3/4 and reversed my trip? Or what if I just stayed here to begin with? Right? Well, how do we draw that? In the homotopy diagram, we draw that like so. In the sense that if I took a slice, say here's 1/4 into my homotopy procedure, well, it's not going to match up exactly with what I just said. So take it with a grain of salt. I think this would be like 3/8 or something, and this would be like times 5/8. But yeah, 1/4 into your process, what you're saying is, I'm going to take F at whatever speed gets me back to x0 after 3/8 of a second. Then I'm going to sit still doing nothing. Then I'm going to reverse, or sorry, I guess I misspoke. This doesn't take me to x0, it just takes me to wherever it got me and then returns the journey. And then I sit at that point doing nothing, and then I undo it. And then similarly, you change little by little in a nice continuous way. Up here, maybe this is 3/4 of the way through. At this point, you're going along F. I think you still take it at double speed technically. Well, how would that? I guess it would help to sit down and write this out, huh? Really what this means when I write F, E, F inverse is I'm thinking about the path F concatenate E, concatenate F inverse. And so it's kind of weird. You have to think about, okay, how do I want to order these? Maybe I want to start by doing F concatenate E and then concatenate that with F inverse. So really one of them is going to go at like quadruple speed. So it's weird, but we don't have to get into the weeds there. It's fine. As long as you trust me that eventually I'd be moving barely anywhere on F, right? I'd take a step along the path, then I'd sit there twiddling my thumbs for 0.98 seconds, and then I'd take a step backwards, right? I'm not doing anything discontinuous or untoward. I'm continuously homotoping my initial concatenated paths to the identity. And you can do that in either direction. This eventually shows that, yeah, those are homotopic, so their homotopy classes are equal. And you could show it the other direction too, right? I could say F inverse times F is also E. But who cares? It's basically the same diagram. Last one, how do we show associativity? And this one I'll just blast through. Here we want to show that if I took F, G, H, associativity means, this is sort of addressing that problem I was just talking about. FGH is equal to FGH. So most students don't catch this unless it's explicitly pointed out, but this really means, so let's sit down and think about this. This means, okay, I'm concatenating these first, right? So let's scoot this over and erase this and say, okay, so here's a question mark. I want to show that's true. This is equivalent to writing concatenate F and G, then take their homotopy class, and then I guess I don't need parentheses at this point, multiply that by H. But that, in turn, is equivalent to saying, well, I already had F concatenate G, now I'm concatenating H. Okay, and looking at this is saying we concatenated these first. So it's like I was spending, if we just focus on this, I was spending half my time at F, half my time at G. Because you traverse F at double speed, you traverse G at double speed, so you're spending a half second traversing each of those. But then I'm like, oh, I have to take this and concatenate it with a new path. So all of a sudden, I mean, I need a whole half second for H. Each of these, I can spend half of that time. So I'm spending a quarter time racing around F, a quarter time racing around G, and then half my time kind of going quickly, but not racing around H. Okay. That doesn't make sense. Sit down with the definition of how I wrote out what concatenation is, that piecewise function. What is this then? This is F times, well, take G and concatenate it with H, and then take the homotopy class. But multiplying those homotopy classes is the same as F concatenate G concatenate H. So the question is really, are these equal? And that's not immediately obvious. This is asking one path where I spend a quarter of my time using F, a quarter using G, and a half on H. Is that homotopic? Can it be deformed into a path where I spend half my time on F, a quarter on G, and a quarter on H? So drawing this diagrammatically, again, who cares about the base point? It's always x0, it never moves. Let's draw it anyway. Okay, and my first path is saying, okay, quarter of my time on H. So let's put a quarter right here, or on F, I meant to say. So here's F, here's a quarter of my time on G, and then a leisurely stroll along H. But then I want to get to here. That's spending half my time on F, a quarter on G, a quarter on H. Okay, and the question is, how do I connect these up? How do I gradually modify this plan of a quarter, a half into half, quarter, quarter? Take a minute to brainstorm if you want to, pause the video. The answer is pretty elegant, actually, after all of that nonsense. Look at this. Right? You just gradually change, and if you look at any one slice you want to look at, say here, you're still always spending a quarter of your time on G, but, right, and that works out because starting out it was a quarter, ending it was a quarter. Great, so keep it the same, right? But you wanted to shrink. Instead of spending a quarter of your time on F, you want to spend more time. And so it's like, okay, I'll just gradually expand to F, spend more and more time there until you're spending half your time. And that time has to come out of H's time. So H, you have to kind of rush. So again, you can think of it as some kind of procrastination. You have 3 tasks that need to get done. And yeah, you could spend, you could race through F and G and then spend your time on H, or you could spend your time on H and then race through G and H. But in either case, you only have a second to complete all of them. So you can continuously vary that as you go. And it all works out. So all that goes to say, the fundamental group of a topological space based at a given point is a group. Right? We have the identity in the sense that, yeah, there's a group element, namely a homotopy class where you do nothing. We have inverses, in that you can always traverse a path backwards. We have associativity in that, yeah, even if you started out going along these concatenated paths at different rates, you can adjust those rates in a nice continuous way. And That gives you associativity. And of course, it's closed. So this is indeed a group. And what does that mean for us? Well, it means if you give me a topological space, and even better, if it's path connected, you don't have to tell me a point. The fundamental group will be independent of that base point. So just tell me a topological space. I can tell you a group associated to that space. After all this work, you're probably like completely lost and your mind is crumbling. So let's see an example, calling it a theorem, but I'm not really going to prove it. I'm just going to show it as an example. The fundamental group of the circle is the additive group of the integers, right? So the integers under addition. Weird, but let's see why. I drew a few circles here. Let's pick a base point. Say that's our x0. We'll start by just using one of these circles, but I wanted to have some duplicates so I could have more drawings on the same page. Okay, so let's think about what kind of paths or what kind of loops I can draw. Okay, first we could do silly loops. I could do the do nothing loop, just kind of sit at x0. Similarly, I could do the loop that, you know, goes around, but then backtracks. Notice I'm drawing the red path off of the circle. Really, it should sit on the circle and then exactly backtrack along the same path. But that prohibits me from drawing directional arrows. So use your imagination. That's a path, right? I could call that F. And that is homotopic to the identity path in the sense that I could gradually deform this thing, make it smaller and smaller until it's the do nothing path. Okay, so this I'm just drawing, let's go back to blue. Here I'm drawing things that are in the homotopy class of the identity. What else could I have done? I could have gone the opposite direction, maybe. And maybe I come back a little and then come back again, and then I come this way and then I do that. A really convoluted path. I'll say it's, you know, this direction. But again, you could imagine if this was a rubber band or something contractible, I could continuously deform it until it's the identity path. No trouble. And just anything like that, right? That always works out to be homotopic to the identity. Now take some time to think, what other paths could I draw that maybe aren't equivalent to the identity path? Pause the video if you want to. The answer is I could traverse the circle like so. Sorry, that was quickly. So I come out this direction, come in that direction, and I've made a full circuit. And the question now is that equivalent to the identity? No, and that might take a little bit of proving. You might not even believe it at first. But how on earth could you possibly take this thing and contract it to the do nothing loop? You would almost have to go outside the space and contract it like this. But I mean, that's outside of our space. Paths have to exist in our space. And I said I'm drawing them slightly off the space, but we're imagining they're absolutely perfect. And so I can't contract it like that, right? There's this big hole in the ground that I can't get over. Or phrased differently, if this was like a cross section of a tree trunk and I wrapped a rope around the tree trunk, how can you bring the rope together into a single point without, sawing through the tree? You can't do it in a nice continuous way without either breaking your rope or the tree. So that's one type of path. Similarly, I could have done dumb things. I could have backtracked a little here, and I could have backtracked, and I could have backtracked that way, whatever, and then eventually I connect up. But still, wiggle that a little, it'll be homotopic to the first path I drew. So no difference between those two. And what else? What if I go the opposite direction? Say I start at x0 and I traverse clockwise. Right? So I go this direction. That's a whole nother path. Again, takes a bit of proving. But there's no way you can, take this counterclockwise path on the middle circle here, right? Go around this way, and continuously deform it so it's a clockwise path. Can't happen. Think about why. And okay, I could deform this little by little as well. Is that everything? Right, so we'll call this, we'll call this, maybe that path was F or something, and this path was F inverse. So in this case, F and F inverse are not homotopic to one another. Neither of them are homotopic to the identity. Is that everything there is? So pause the video if you want to. The answer is no, there's more. What if you did this? What if you wrapped your rope around the tree twice before coming back to your starting point? Again, I'm drawing it in the center. Imagine it's around the blue border. So I wrap it twice, right? I say, ring around the rosy, pocket full of posy. And there we go. That's, again, fundamentally different. I can't like undo one of those windings to get to a single winding. So that's a totally different kind of path. The double loop. And similarly over here, loop once, loop twice, and come back. Totally different from looping clockwise once. And I could keep going. I could do it 3 times in either direction, 4 times, as many times as I want. And I would get fundamentally different paths. So all of a sudden, this is seeming like a pretty complicated space. Like, man, we have a lot of different homotopy classes, right? But it actually works out to be fairly nice. And I mean, since I already spoiled the surprise, the fundamental group is the integers. So instead of calling this E and F inverse, let's erase the double circuits for a second. This is really the homotopy class of 0. This is really the homotopy class of 1, because I looped once clockwise or counterclockwise. This is the homotopy class of -1, because I looped once clockwise. If I reproduce this down here, hopefully you can guess what I would get if I went twice in either direction. So let's erase. We have. So here, what direction was I going? Counterclockwise. Counterclockwise twice, or clockwise twice. Sorry for the terrible drawings, but you don't mind. Well, this is the same as the number 2. This is the same as the number -2, and you could keep going. That's the connection to the integers. And why does it work out? Why does it turn out that these groups are the same, right? To verify that 2 groups are equal, you would have to find a homomorphism between them, right? An isomorphism between them. So a homomorphism that's bijective. And you can sit down and do that. You actually can. You can say that, and here's the mind-blowing thing. You can say that the group structure on this fundamental group of homotopy classes of loops is the same group structure you get on the integers under addition, in the sense that, if we think back to this being F and this being F inverse, F compose F inverse as an equivalence class is in some sense, draw like this, the same as 1 plus -1. And what's 1 plus -1? Well, that's 0. And what happens if I concatenate F with F inverse? Well, if I go this way, and then I go this way, I've undone everything, right? It's like saying, here's a loop of string. I can contract that to a point, right? That's homotopic to 0. That's homotopic to the identity. We showed that a second ago, that yeah, inverses actually work as you would expect. So E really is like the 0 element. And what if I did F concatenate F? That's sort of like saying 1 plus 1 is 2, right? Because this was actually like the equivalence class of, I don't know, maybe call it 2F or something. The idea being, yeah, if you loop around twice, that's exactly this, but that's the equivalence class of 2, right? So I could say that you could teach kindergartners how to add integers by having them loop string around a tree. I could say, hey Johnny, what's 2 minus 5? And I would, give him a long piece of rope, and he would run around in one direction twice, in the other direction 3 times or 5 times, and he'd be left with 3 loops in like the clockwise direction. And he would be like, oh, 3 loops clockwise means -3. And then I'd be like, Sally, what is 0 plus 7? And she would be like, oh, well, 0 means I just stand here at the base of the tree. And then 7 means I go around 7 times. And what am I left with at the end? Well, 7 loops around in the counterclockwise direction. That's the number 7. And you literally get, I mean, it's a bijection. It's a 1-to-1 correspondence between loops around a tree, or homotopic paths on a circle, with the integers. And it takes a bit of extra machinery to prove this, something you might encounter in an algebraic topology course. But I think it's a truly beautiful result that instead of adding integers the normal way, you can think about it as wrapping loops around a circle. So that's it for today. Thanks for watching.